Welcome to this presentation. We are now resuming max pooling with Vision Transformers Reconciles class and Shape in Weekly Supervised Semantic Segmentation by
Simone Rossetti, Damiano Zappia, Marta Sanzari, Marco Scherf, Fiora Pirri.
Weekly Supervised Semantic Segmentation task consists of objects pixels inference using cheaper supervision than segmentation masks. We use class labels as they are the cheapest annotation possible. The method we propose is named ViT-PCM. At training time, we infer categorical distributions over the input pixels. We aggregate the predicted output using the global max pooling operator, which produces a multi-label prediction for the input image. We optimize the network's parameters, minimizing for each category K the binary cross-entropy error to the multi-label ground truth. At evaluation time, we apply the orgmax operator to the output pixels categorical distributions to get pseudo-segmentation masks for each category. We compute the mean intersection over union with the ground truth semantic segmentation masks for assessing the pseudo-masks quality. Our network decomposes the image into patches, adding positional information not to lose the spatial structure of the input. After, it computes multi-head self-attention over the patch sequence to encode semantic relations. We use Vision Transformer in this patch encoding step. At this point, we map each patch into class probabilities. We reshape the sequence back to preserve the original input structure. The global max pooling operator returns the maximum likelihood of a class to be present and creates a direct patch to class mapping. This method, namely method 1 in the slide, is straightforward yet very effective in localization. We noticed from our experiments that this method suffers from sparse outliers and low to medium confidence due to high intra-class variance. For this reason, we introduced a second method which conditions each patch on the column and row ancestors. This method results in more consistent shapes and higher confidence, particularly at the borders. Finally, to induce task equivariance, we design a two-branch architecture where the two networks share the same parameters and the optimization maximus their output similarity. We apply color augmentations and rotations to the input batch of the first branch, while we also use random cropping, scaling, and context mixing in the input batch of the second branch. This last augmentation helps in creating object representations independent of the context. As Table D shows, at the expense of more significant initial complexity, our approach uses fewer parameters as shown in the figure at the bottom and achieves state-of-the-art results on two benchmarks, PascalVOC 2012 and MS-COCO 2014. Table A confronts the mean intersection over union accuracies of the baseline pseudo-masks on the PascalVOC trained set with and without conditional random field refinement. Table B shows the accuracies of different segmentation networks trained on the generated baseline pseudo-masks with the respective methods. Notice that those on top use an additional refinement loop on the baseline pseudo-mask, which doubles the time and parameter requirements and reduces generalization since it biases the learning on the CRF hyperparameters. In Table C, we report results on MS-COCO 2014 val set. We trained DeepLab segmentation network with ResNet backbone on our baseline pseudo-masks. Here we show some qualitative results on PascalVOC 2012 and MS-COCO 2014 val sets. We acknowledge DeepLinks, which granted and sponsored this research.